We're going to begin this lesson, though, talking about the first type of probability. I told you there were three types. The first one that we're going to talk about is experimental probability. All right? And experimental probability, the way that we calculate an experimental probability is whenever we do this. So by definition, experimental probability is when you gather data, or data, however you want to pronounce it, from observations. Okay? From observations, you can calculate experimental probability. So the way I write that is EXP PRB. All right, so we're going to do a little experimental probability right now. All right? Matt in the back has how many balls, how many paper wads do you have back there? You have 5? Okay. So here we go. So what we're going to do is we're going to keep track here, all right? Matt, so the trash can's up in the front, so go ahead and throw your first one here, okay? He missed. He is 0 for 1, okay? He is 0 for 1 here, okay? Go ahead. Okay, he is missed. He's 0 for 2. He's 0 for 2. Okay? Go next one. He missed it again. He is 0 for 3. Come on, make one. Come on. Oh, man, he's over. Okay. Okay, time out. We're going to pause right here. Shh. We're going to pause right here. Okay? So right now, the probability of Matt, okay, making his next shot. So let the record show. I know that people at home, if you're watching this, you can't see this, but Matt just threw 4 shots from about 12 feet away and he missed them all. Okay, so how many times has Matt gone to throw the ball? He's gone 4 times, and how many has he made? He's gone 0. So what is the experimental probability that Matt is going to make his next shot? It's 0. Okay, let's see if math is correct. Let's go, Matt. Come on. And, oh, we were right. He missed all 5. He missed all 5 right there. Okay, so what are we doing here? What we're doing is, this is an example of experimental probability, right? We were gathering data as we went, and we used that data to make a prediction for the next one. Okay, so what do we do here? How do we? So let's write down what we did. Okay, so the probability of an event happening for experimental probability can be calculated by the number of times the event happens, the event occurs, divided by, what did we do? What did the 4 represent? The number of trials that we've done, right? Yeah, P stands for probability of an event, okay? So the probability, this P stands for probability of the event happening, can be calculated by the number of events that have occurred divided by the number of trials, okay? This should look very familiar to you in the form of like batting average, right? When we do a batting average, that we're calculating their experimental probability, right? Because we're taking their number of times at bat over, right, or number of times at bat at their trials, and then versus their hits. Does that make sense? So this comes up in sports a lot, right? Does that make sense to you, Flo? Okay, so along those lines, let me give you an example for number 2 here. Okay. Okay, here we go. So here's a very simple, straightforward example. We've got a quarterback has completed the last 30 of 40 passes. What's the experimental probability he'll complete the next pass, right? Do you see why this is experimental probability? Yeah. Because we're judging this based on trials, right? So we have 40 trials. He's completed 30. So the way that we would write it out is, well, we would say, well, the probability of completing a pass on his next pass is going to be the number of times that the event occurs, 30, out of the number of times that we've had tries to do it, which is 40. So he has completed 30 of 40. So the experimental probability for his next pass would be 3 out of 4, or what would that be, everybody? 75%. All right, does that make sense? 75%. Okay. Not really a big deal. Kind of straightforward, right? But that does lead us into the 2 ways. So there's a third box here. You can go back to 100%. Okay. You need that back again? Okay. There we go.
Can I have the purple?
Okay, there you go. Yeah. Okay. So let's talk about what are the ways that we can represent probability. Yeah, the first way, right, is a fraction. Okay, but hold on a second. Let's stay on fraction for a second. On that fraction or the ratio, right? What are your parameters for your fraction? Can I have 7/5 be my fraction? Why not? Why can't 7/5 be my fraction? If it's a fraction, then our fraction must be between 0 and 1. Yeah, 0 and 1. I thought my notes are backwards. So it's if my fraction is between 0 and 1, then there's the probability that it could happen. What if my fraction was equal to 1? That'd be 100%, or that would be an event that is guaranteed to happen, right? What about if my fraction was 0/5? Yeah, then that's not going to happen. Kind of like Matt making that shot earlier. I was 0/5. Yeah. Yes. Yes. The other way that we could do it is by a percent, right? But what are our parameters of a percent? Can I have like a 700% chance something happening? No. 0 less than or equal to x less than or equal to 100%. Right? If something has a 0% chance of happening, that means it's not going to happen. If there's a 100% chance of it happening, that means that is definitely going to happen. Okay? All right, here we go. I wrote the quadrant out. You missed that last one, by the way. Okay. A softball player hits 20 of her last 50 times a bat. What is her experimental probability she will hit her next at bat? 20%. Okay. Okay, I want the math behind it. So how are we going to set it up? Nick, what are we going to do? Probability of what? What are we taking the probability of?
Hitting the ball.
Yeah, the probability of getting a hit, right? Okay. Is going to be the number of times the hit has happened, which is 20.
Yeah, over the trials.
Out of her trials, which is 50, which is 2/5, which is 40%. Okay? There we go. So I'm going to show you how to use your calculator to simulate and design an experimental probability. Okay? So here is the scenario. Before we touch our calculators, let me give you this scenario out here. So no calculators in hands yet. Here is the scenario, okay? You're going to take a multiple choice test. We all love multiple choice tests, right? Actually, I don't like them, but they're out there, okay? No, I'm going to show you how to design one using your calculator, James. Okay? There's a multiple choice test. There are 4 options. You can either A, B, C, or D. This is kind of standard. We've all taken a multiple choice test where there's 4 questions, right? Okay.
4 answers.
Oh, sorry, 4 answers. Thank you. If you score greater than or equal to 60%, we're going to say that you passed the test. Now you could bump that up to 70 if you want, or 80 if you want, by making it 60%, okay? If you score more than 60% or more, you pass the test, okay? And there are a grand total of 10 questions, okay? I think about when I had to take my motorcycle driving test, right? I took my license. Well, no, I had to take the test. I just wanted to go see if I could pass. I took the class and I studied for it, and this was very, very similar. I think there were 20 questions, and there were 3 answers. There were 3 answers, there were A, B, and C. Yeah, I passed. Yeah. Okay, so the story goes, we're going to take this test. It's going to be 10 questions. There are 4 choices. You need 60% to pass, okay? If you just guess, let's say you don't know any of the answers, you strictly guess, all right? What I want to do is I want us to figure out if you took the test 20 times, how many times you would actually pass. Okay? 20 times. Okay? So here's what you're going to do. You're going to make a chart. Okay? So this is going to be number of times taken. Okay? And this side is going to be, you're going to number 1, 2, 3, all the way down to 18, 19, and 20. Okay? Over here on this side, you're going to tell me whether or not you get your percentage, okay? Your percentage points. And what are you looking for? You're looking for greater than or equal to what? 60%, okay? So I'm going to show you how you can design this experiment using your calculator. Yeah, I want you to do. I'll do the first couple for you. I'll do the first 3 with you. You guys do 20. It's very, very quick because our calculator can simulate this for us. But I want you to keep track, and then as a class, there's like 17 of us in the room right now. I want us to figure out if we each took this test 20 times, how many times we would pass, and calculate sort of its probability that we would do that. Okay? The experimental probability on the next time that we would take it. Okay? So here's how it works. I want you to take your calculator up. Okay? And what we're going to use is we're going to use the feature called RandInt. And what that stands for is a random integer feature. All right? Now I'm going to show you how to plug this in. We're going to go 1, 4, 10. So what does this mean? What does this represent? What do you think the 1 represents? The 1 represents the fact that every time your calculator generates a 1, and I'll show you this. I'll show you an example. Every time your calculator generates a 1, that means you got it correct. Okay? So we're asking the calculator to generate random integers from 1 to 4 10 times. So every time we run an experiment, it's going to give us 10 numbers from 1 to 4. And that's going to simulate us guessing on all the 10 questions, right? Okay? Every time we get a 1, it's correct. Every time we get a 2, a 3, or a 4, it'd be incorrect because there's only one correct answer. So let me show you how this works. So on the calculator, bring up the calculator for us. Okay? Here you go. You're going to go to the math button. No, it's okay. You're going to go over to probability. And that's what we're talking about. And you'll see option number 5 right there. See how it says random integer? So we're going to push option number 5. Now your calculator might look a little different. It might actually just say RandInt, depending on what version you have. I will help you individually, but let me get you started, okay? So we're going to go, the lower bound is 1. The upper bound is 4. So that means generate an integer from 1 to 4 10 times. That's what that means, okay? Math probability 5. Okay. If yours does not look like this, just sit tight. I'll come around and help you out. It won't take very long. I want you to show you. Okay, here we go. So I'm going to push this. I'm going to push enter. And look, I'm back to this screen here, right? I have 1, 4, 10. So when I push enter this time, this simulates me taking the test, and I did not get a single answer correct. How do I know that just from looking at it? There's no ones, okay? I'm defining a 1 to be a correct answer. So the first time I took this test, I got how many correct? So I would put 0% in this column for number 1. Of course, yeah, you guys are going to be all different. It's out of 10, so... Okay, well, if I don't take the test again, I just push enter. It does it for you. Oh, now look at this one. Look, I got the 3rd question right. I got the 5th question right. I got the 8th question right, and the 10th question. I got 1, 2, 3, 4. What's my percent? 40% because it's 4 out of 10. Right? Does that make sense? So this would be 40%. Okay? All you're doing is generating a list. You guys do it 20 times. See how many times you pass. What do we call a pass? 60% or better. Okay, you guys go ahead. So did anybody pass after 20 times?
I passed.
I have 1 person, 2, 3, 4, 5, 6 of us pass. How many times did it take you in order to pass? 18? 16?
Oh, I just passed.
Yeah, and I just passed. Okay, so bottom line, this is really hard to do, right? So don't show up to a quiz and just guess because you're more than likely not going to pass. Or you need to take that same quiz, I don't know, what, 18 times or something before you just got past it if you just guessed every single one, right? So, interesting question, I thought. Let's talk about this word here, this idea called sample space. This plays a big role when we're talking about probability. What is a sample space? Anyone heard this term before? Nick, you think about it? Do you know what this is? Sample space? No. A sample space, okay, is this. The definition for sample space is the set. So this is important. So it's a collection of objects, a collection of things. It's a set. It's a set of all possible, equally likely outcomes. Alright, this is very important. The sample space is the set of all equally likely outcomes. This plays a giant role in discovering what's known as theoretical probability, which is what most people calculate when they're taking a probability, alright? So let me give you an example of rolling the die, right? This is the one that leads off for sample space. The sample space for rolling a die has to be the set of all possible outcomes. So give me a possible outcome for rolling a die. A 1, give me another one. A 2, give me another one. A 3, a 4, a 5, or a 6. Okay, there we go. Doesn't matter what order they're in because they're all equally likely, right? So the sample space consists of 6 elements, right? When you roll a die, you're guaranteed to get one of these numbers on the top die, right? You can't get anything else. You can't roll a 2.5. You can't roll a 7, all right? Unless it's some crazy wacky die. But a standard normal die, the sample space would be these elements right here, all right? So now that leads us, why do we need that? Because let's say I want to figure out the probability of rolling a 2, right? The probability of rolling a 2 on a die is going to be, what's the probability? Everyone knows this one. What is it? It's 1 out of 6, all right? So what does this 1 represent? Why is there a 1 there? Yes, number of favorable outcomes, right? Okay, it's a fraction. What does this 6 represent? The number of the total outcomes, right? Okay, so do you realize that the total outcomes is the same number as the number in our sample space, right? There are 6 elements in our sample space right there. So most people really understand the probability of rolling a 2 is 1 out of 6 because of this. And what they're stumbling upon is this idea for number 7, which is exactly what's known as theoretical probability. Theoretical probability. Okay? And we represent it the same way. So the probability of an event is just what we wrote up there. It is a fraction. It's the number of favorable divided by the number total. So here's a question I could ask on a test or a quiz. What's the difference between theoretical probability versus experimental probability? Or is there even a difference? All right, let's do an example for theoretical probability. Let's do this. I'm gonna roll 2 die. Okay, what's the probability that the sum of the die is going to equal 7? The probability that the sum is equal to 7. I'm gonna roll 2 dice. Yeah. What's the probability that the numbers on top add to 7? Okay. This question is a classic probability question because it answers the question about why people think 7's a lucky number when they have 2 dice. I'm going to show you right now why they think it's a lucky number, okay? Okay. Okay. So here's my first die. I'm going to go, so 1, 2, 3, 4, 5, 6, right? That's my first die. I'll say that one's blue, right? And then I have this other die that's purple. 1, 2, 3, 4, 5, and 6, okay? And then the green, or I'll actually go pink. The pink is going to represent the sum of the 2 die put together. So if I rolled a 1 and a 1, I would have a grand total sum of 2, right? You guys agree with that? If I rolled a 2 and a 1, I'd have a 3. This would be 4. This would be 5. This would be 6, right? If I rolled, and then this last one would be a 7. Everyone know what I'm doing so far? Does that make sense? Yeah? Okay. Well, if we keep going with this, right? Well, this would be 2. This would be 3, right? 2, and this would be 4. This would be 5. This would be 6. This would be 7. This would be 8, right? This would be 4, 5, 6, 7, 8, 9. All I'm doing is adding the numbers together, right? So 4 and 1, that's going to be 5. 4 and 2 is 6. 4 and 3 is 7. 8, 9, and 10. Now let's just finish this off, right? This is going to be 6. This is going to be 7, 8, 9, 10, 11. And this will be 7, 8, 9, 10, 11, and 12. So for example, there's only one way to roll a 12. I have to roll a 6 on my blue die, and I have to roll a 6 on my purple die, right? That's the only way I could get a sum total of 12 for that. Well, do you realize what these numbers right here represent? What do they represent? The sample space. Very good. These numbers right here represent my sample space. Okay? And what is the total number of elements in my sample space? I have a grand total of 36 elements in my sample space. Okay? Now, 7. The probability of the sum is 7. Well, that's represented by this one, this one, this one, this one, this one, and that one there. All those highlighted circles, right? Well, how many of those are there? Yeah, there are 6. And you'll also notice that there are that 7 occurs 6 times, right? It's the most out of any other combination out there, right? A 6 only occurs 1, 2, 3, 4, 5 times, right? A 12 only occurs once. So the probability of the sum is 7 is greater than the probability of the sum being any other number from 1 to 12. Well, actually from 2 to 12. It can't be a 1, right? So 6 out of 36 is equal to, what, 1/6? Is that right? And that is approximately 16.72%. So you have a 16.72% probability rolling a sum of 7. And that is your highest probability out of all of them right there, right? What's the probability of rolling a 12? 1 out of 36, which is what? What would that be? I said, is it not 16 points? What is it? 16.6 repeating? I don't know. Okay. You guys good with that? You okay with that? Okay. All right. So what's 1 out of 36? What's the percentage? What's our percentage? 1 out of 36. 4.15?
No.
2.7? 2.8? So we have a 2.8% chance of rolling a sum of 12, right? Okay. This was my favorite class I took in college, combinatorics class. Yeah. It's a crazy word, right? This is where you get really good at counting things, right? So I'm gonna write down an example here because it takes a while, and then we'll talk about it. So let me write it out for you. Okay, yeah, big question here. Okay, we're gonna determine the theoretical probability of being dealt exactly 2 aces from a standard deck of 52 playing cards for a 5-card hand. So, anybody ever played poker like with their parents or with their uncles or something like that? When you play poker, right, you're dealt 5 cards. 1, 2, 3, 4, 5. There's lots of different varieties of poker, right? Texas Hold'em, right? So what we want, you can get a 3 of hearts, for example. You could get a 7 of diamonds, for example. You could get the ace of hearts. You could get the king of spades, right? That's kind of a funky spade. Or you get, like, I don't know, the 2 of clubs, right? Something like that. So that's a 5-card hand right there. It's a very bad drawing, but you understand what I'm saying, right? The 2 of clubs. Okay? So what we want, right? We want to understand, how do we talk about the theoretical probability from, this is a really tough question, of being dealt exactly 2 aces. Is that called pocket aces? That's right? You have 2 aces? Pocket aces? Okay.
Yeah, pocket aces is in Texas Hold'em.
Okay. So we want this, right? So we want to know the probability of exactly getting, like, let's say this was the ace of diamonds, for example, okay? So what is the probability that we would be dealt 2 aces from a 5-card hand of a regular 52-card deck? Okay? So here's what I want you to do. I want you to talk to someone sitting next to you. Figure out, what do you think we would need to know? What would be important here? So on and so forth. Get everything you can think about out on the paper right now, and then we're actually going to figure it out together. Okay? For this, we know, I love this problem because it has to do with 3 elements that we've already been introduced to. Okay? We know that our answer is going to be a fraction. Is that true? Our answer is going to be a fraction, right? You think you know? What is it? 425. Okay, all right. If we're calculating a theoretical probability, then we need to figure out the sample space, right? The sample space consists of what? Well, what is in that sample space, right? Is this right here, is this one member of our sample space right here? Yeah, because that is exactly, right, one combination of 5 cards. So let's think about this, right? How many cards total are in the deck? So, 52. How many do we want to combine from those 52? 5, right? Check this out, you guys. I do not know what this number is. I have no idea what that number is. I'm assuming it's a pretty big number, right? I don't care what that number is. What I really care about is what that number represents. That little formula right there, 52 combined 5, is a very powerful statement because that allows you to count how many ways you can randomly grab 5 cards from 52. That's what you need to understand. You don't need to know what that number is. You need to know what that number means. All right? So far, so good? So that right there is our total. 52, choose 5. That right there represents all the ways that we can randomly grab 5 cards from 52. Does everybody buy that so far? That's our denominator. Do you realize why that's our denominator? Okay, I'll pause it and start with it. All right, now we got to build the top. All right? Let's think about our cards. 1, 2, 3, 4, 5. We're going to get dealt 5 cards, right? Okay, what do we want? We want these 2 cards to be what?
Aces.
We want these to be aces. These 3 other cards, what do we want? Yeah, not aces, right? Okay. Yeah, the problem says exactly 2 aces, right? So that's what we want, right? We want exactly 2 aces. So those first 2 cards, oh, well, they could be anywhere, but we're just saying for right now, we want 2 of them to be aces, right? How many aces are there? So this is another combination problem. We don't care which 2 aces we get. We just want 2 of them. So there are 4 aces in a deck, and we want to choose any 2 of them. Again, I don't know what that number is. I mean, that one's pretty easy. I do know. But I'm going to pretend I don't know what that number is, right? I just have to know what it means. It represents all the possible ways we can combine 2 aces from the 4 in the deck. So far, so good? Rachel, you go with that one? Okay, those other ones. How many are left over that we don't want to be aces? 48. Very good. Why 48? There you go. And from these 48, we want to combine how many? 3. Great. And the fundamental counting principle says that we do what to these 2 numbers at the top? We multiply them together. So check that out. We have employed all 3 things that we've talked about in this class. The fundamental counting principle, combinations, and theoretical probability all in one. All right? I don't know what that number is. Your calculator sure does. This is why it comes in handy. Okay? So let's figure this out. We want 4, choose 2. We want to multiply that by 48, choose 3. We want to divide that by 52, choose 5. We want to plug this into our calculator, and we're going to get a percentage. Everybody ready to do that right now? Good. This is about 4% when you all say it's said and done. That's about exactly 4%. That's a really powerful piece of information right there.